Euler's number e. One reason it's important is if you study the exponential function e of x. The derivative of this function is equal to the function itself. We will not prove this here, but just accept that this is the case. If you take any other number than e, this will not happen. That's one reason e is so special. For a general number a, the derivative is instead given by this, so you have to also multiply it by the natural logarithm of a. Remember that ln means log e. So the derivative of this one is equal to itself, but also multiply with the constant. And this constant is only equal to 1 if a is equal to e. Using this, one can prove that this must be the case. A number a can be written like e ln a. This just follows from the definition of the logarithm, because this means what should you raise e to the power of to get a. And here you just have e raised to that, so by definition this is equal to a. Then we can write this using this as this, which in turn can be written like this, using this rule of calculation. Then we have that this can be written as this, and this is just the composition of two functions. So here we have an outer function e to the something, where the inner function is equal to ln a times x. So if you take the outer derivative first, then according to this rule it's just this, and here we have to put that one. Then we have to multiply by the inner derivative, and here is just a constant times x, so the inner derivative is ln a, the constant. And now we see this one stands here, and that was equal to ax. So this is just ax. And then we have shown that this is equal to this, which is what we wanted to prove. So say that we want to calculate the derivative of this one. First of all, we can note that here we have one function, which is multiplied by another function. So if you first use the rule for derivative of products, we should first take the derivative of the first one times the second one, added to first taking the first one and then multiplying by the derivative of the second one. Now this is just 2. Here we can use that this is a composition of two functions. We have the outer function e raised to the power of something, and the inner function 3x. So first we have the outer derivative, e raised to the power of something. Then we have the inner derivative, which is just the derivative of this one, which simplifies to this, which we can write as this if we factorize out the 2 and e raised to the power of 3x. We're now going to find the antiderivative of this one. If this were not here, this would be very simple. But this complicates things. However, if we use integration by parts and identify this as f of x and this as g of x, then first of all we should take the antiderivative of the first one, but that's just the function e of the x. Then we shall multiply g, which is just x. So here this is capital F, and this was g. Then we should have capital F and g prime, and capital F is again e raised to the power x, and g prime is just the derivative of this one. This one we can also write like this, and here we just need to take the antiderivative of that, but that's just e raised to the power x. Since you take the derivative of this, you get the same back, and then also, of course, then must be its own antiderivative, then plus c, which finally can be simplified to this. As we have seen earlier, the antiderivative of 1 over x is the natural logarithm of the absolute value of x plus a constant c. And that means if you take the derivative of this one, you will get this one. So if you take the derivative of this one, you will get this. And if you limit yourself to positive x, then we can just write it like this instead, because then this is positive, so we can drop the absolute value signs, and this is just equal to that. If you want to take the derivative of a logarithm other than the natural logarithm, then that is just given by this. So instead of having just this, you also get the constant in front. And this one can be shown using this, similarly to how we showed for the exponential function. According to one of the logarithmic rules, we have that this can be written like this. And here, this is just ln x. And this is just ln a. So taking the derivative of that one is the same as taking the derivative of that one. But this is just ln x divided by constant. So we can take the constant in front, and the derivative of this one is just 1 over x. Then we see that the derivative of this is equal to this, and this is what we wanted to prove.